Welcome, focused learners, to this complete step-by-step masterclass on optimal physical automation. Today, we're acting as rigorous academics, and I'll be guiding you through a comprehensive university-level explainer on advanced control loops. We are moving decisively beyond traditional feedback. It's going to be a deep dive, and we're going to explore this so that every single engineering mechanism, mathematical proof, and operational paradigm shift is thoroughly understood. So, get ready. Our explainer today is structured as a clear journey through three critical sections. First up, Section 1, the boiler paradox. Then, Section 2, feed-forward and combined strategy. And finally, Section 3, mathematical proof and synthesis. Okay, let's dive right into this. We're starting with Section 1, the boiler paradox. We're going to uncover a fascinating engineering dilemma where traditional feedback control doesn't just fail, it actually causes catastrophic system collapse. Announcing Slide 1. Let's meticulously examine this blueprint of a complex industrial reactor. Notice the primary reactor vessel, labeled R101, right in the center, and it's flanked by these complex heat exchangers, E203, over on the right. Now, if you look at the piping, incoming raw materials and external disturbances enter from the bottom left, flowing through the main pipeline past valve CV307. We can clearly trace feedback loop 1 in orange. The sensor array sends signals back to the PID-FB controller, which then attempts to regulate valve CV305. But more importantly, look at those cyan blue lines representing feed-forward path A. Here, disturbance sensors bypass the main loop entirely. They feed data into the advanced FF call controller to preemptively adjust the FF actuator. Every physical connection, every single valve, and every sensor block you see here establishes the very real-world engineering stakes we are about to optimize. Moving to Slide 2. This brings us to a fundamental insight. Single variable feedback control is completely reactive. By definition, an error absolutely must exist before the controller generates a corrective command. Let's trace this flowchart from left to right. First, a physical disturbance occurs. This leads directly into that red box, a mandatory time delay. Because of this delay, the system output deviates from the set point. You can see that represented by the dip in the graph there. Only then does the controller finally act. This literally proves that traditional feedback is fundamentally trapped in a reactive cycle. On Slide 3, we see that when looking beyond single variable feedback, modern engineers have quite a few advanced strategies at their disposal. The bullets list them out: feed-forward control, feed-forward/feedback control, cascade control, time delay compensation, and decoupling control. However, notice the glowing cyan highlight. Our specific focus for this masterclass will be on mastering pure feed-forward control and the optimal feed-forward/feedback combined control. Let's examine the physical challenge on Slide 4. Maintaining boiler liquid level. What we have here is a large, horizontal, cylindrical boiler tank. At the bottom left, a water inlet pipe supplies the liquid. At the very bottom center, you'll see a coiled heat input that boils the water. Up at the top, a pipe carries the steam output away. That horizontal dashed line right across the middle, that represents our target set point for the liquid level. The objective here is incredibly strict. Maintain that liquid level to prevent overheating if it drops too low, or prevent liquid carryover into the steam turbines if it gets too high. The physical stakes here are absolute. So let's look at Slide 5, which introduces our first architecture, Standard Feedback Control, or FBC. The mechanism described in the text here is purely reactive. The level transmitter, or LT, measures the output, and the level controller, or LC, adjusts the inlet water valve based entirely on the set point error. Just look at the engineering connections on the diagram. The LT sensor at the top right takes a physical reading of the water level inside the tank, and it sends an orange dashed signal over to the LC. The LC then calculates the error and sends a command down to the actuator on the water inlet valve at the bottom left. To understand why this fails, look at Slide 6, Identifying the Disturbance. We have to understand a fatal flaw here, laid out in our bullets. First, boilers possess remarkably low liquid capacity relative to their massive steam output. Second, the variable steam demand acts as a severe, rapid disturbance that fundamentally destabilizes the liquid level. Look closely at the massive glowing red arrow on the right side of the boiler, right by the steam output. This denotes our unmeasured disturbance. When downstream demand suddenly spikes, the steam is literally sucked out of the boiler violently. Now, what's really interesting about this slide, Slide 7, is the highly counterintuitive physics of the swell phenomenon. Increased steam demand suddenly drops tank pressure. As a result, subsurface boiling increases, expanding steam bubbles, and the surface level temporarily rises even as water mass is actually being lost. Let's sequentially step through all three of these diagrams. In diagram 1, demand spike, steam rushes out. In diagram 2, pressure drop, the internal pressure pushes down less, causing bubbles within the water to suddenly and rapidly expand. Finally, in diagram 3, the swell, this bubble expansion pushes the physical surface of the liquid up, creating a massive red arrow pointing to a false high level. And here on slide 8, we witness the total failure of feedback. Because the sensor reads an artificially high level, the controller makes a dangerous, incorrect decision. High-gain feedback in this state causes severe system oscillation. Let's systematically trace this incredibly dangerous flowchart. First, the LT reads high level, which is a false positive. Second, the LC calculates a positive error. Third, the LC blindly follows its programming and commands the feedwater valve to close. This leads directly to the disastrous red box result at the bottom. The boiler is starved of water precisely when maximum steam is demanded. Disaster. Which perfectly tees up Section 2, Feedforward and Combined Strategy. Having just witnessed the catastrophic collapse of reactive systems, we're now going to shift our entire paradigm and design a preemptive shield to solve this exact physical crisis. Introducing Slide 9, our second architecture, Pure Feedforward Control, or FFC. This requires a massive paradigm shift. As the text states, do not wait for the liquid level to change. Measure the incoming disturbance directly and take preemptive action before the error even occurs. Let's contrast the two diagrams shown here. On the left, feedback control is depicted as a slow eye, measuring the output inside the tank, which we know is purely reactive. But on the right, feed-forward control is depicted as a fast shield. The eye is now measuring the disturbance directly at the steam output pipe, acting preemptively before the tank level even has a chance to fluctuate. On slide 10, diagramming feed-forward in the boiler, the mechanism is simple but absolutely profound. The flow transmitter, or FT, measures the rapid steam fluctuations. The controller preemptively adjusts the inlet valve, and the level transmitter is completely removed. Looking at the block diagram, an FT sensor on the top right measures the steam leaving. It sends a cyan-dashed signal directly to the FFC block, which instantly routes a signal down to actuate the inlet valve. Notice that the old level transmitter is entirely gone. We are flying on mathematics alone at this point. So, the crucial point is captured here on slide 11, the elegant logic of mass balance. If X kilograms per second of steam leaves the system, the controller immediately commands the valve to supply X kilograms per second of water. The mathematical disturbance is neutralized before the liquid level dynamics are ever affected. The visual scale on the slide perfectly balances the cyan steam flow out block on the left, our disturbance, with the white feed water flow in block on the right, our manipulated variable. However, looking at slide 12, we must acknowledge the blind spots of pure feed forward. By tracing this open loop diagram, you see the FFC sends a signal to the plant to produce an output, but there is no line returning from the output back to the controller. It is fundamentally open loop. Therefore, we find three distinct warning boxes or vulnerabilities. First, unmeasured disturbances. FFC simply ignores any leak or unmeasured pressure change. Second, mathematical inaccuracies. It requires a highly accurate dynamic model of the plant. Third, steady state drift. Without an output check, minor calculation errors compound over time, eventually emptying or overflowing the tank. To solve these blind spots, we introduce Architecture 3 on slide 13, the combined strategy. In this model, as the text outlines, feed-forward acts as the primary shield against rapid load changes, preventing shrink and swell errors, while feedback acts as a slow, continuous trim to guarantee the set point is maintained over time. The puzzle pieces here brilliantly illustrate this synergy. The cyan piece on the left is feed-forward control, providing speed and handling massive disturbances. The orange piece on the right is feedback control, providing precision, trimming drift, and handling unmeasured errors. Together, they interlock to form the white diamond of optimal automation. Let's look at slide 14. When diagramming the combined loop, strict engineering logic dictates that the final control element, the valve, can only receive one command. The outputs of the FFC and LC are mathematically summed prior to actuation. Visually tracing the loops here, the orange LC feedback loop and the cyan FFC feed-forward loop both converge on a circular summation block, represented by the Greek sigma symbol. They mathematically combine their corrective efforts into a single, perfect command sent directly to the feedwater valve. Now, focused learners, we advance to Section 3, Mathematical Proof and Synthesis. We are now going to translate our physical triumphs into rigorous mathematical proofs to guarantee these systems work on paper just as flawlessly as they do in the physical plant. Turning to slide 15, to prove the combined system works, we must translate every physical instrument into the Laplace domain. Let's read through these. The boiler tank translates mathematically to plant dynamics, G subscript P of S. The control valve translates to actuator dynamics, G subscript F of S. The LC, in orange, translates to the feedback PID controller, G subscript C1 of S. The LT translates to the output sensor, G subscript M1 of S. The FT, in cyan, translates to the disturbance sensor, G subscript M2 of S. And finally, the FFC translates to the feedforward controller, G subscript FF of S. Building on these translations, slide 16 gives us the complete system block diagram. Let's move to it and see how this builds. This architecture explicitly separates the reference set point tracking from the unmeasured disturbance rejection. Let's carefully trace every single mathematical block and signal path here. Starting on the far left, the set point YSPS enters a summing junction, subtracts the feedback signal, and moves into the feedback controller GC1S. From there, it enters a second summing junction. Simultaneously, on the top right, the disturbance DS follows path A into the disturbance dynamics GDS. But DS is also measured by GM2S and passed into the feedforward controller GFF along path B, which feeds a positive signal into that central summing junction. The summed signal then passes through actuator GFS, becoming manipulated variable MS, which enters the plant GPS and combines with the disturbance effect to yield our final output, YS. That output is then looped all the way back through the sensor GM1S. On slide 17, deriving the system output, we state that the total process output, Y of S, is the superposition of two independent actions, responding to the set point and reacting to the disturbance. Let's derive this complex equation step by step exactly as shown. Y of S equals the first bracketed term, which is the numerator, GP times GF times GC1, over the denominator, 1 plus GP times GF times GC1 times GM1, and all of that is multiplied by YSP of S. This entire orange bracket represents tracking the reference set point. This is added to the second bracketed term, which is the numerator, GD plus GP times GF times GFF times GM2, over the denominator, 1 plus GP times GF times GC1 times GM1, and all of that multiplied by D of S. This cyan bracket represents reacting to the load disturbance. Now, slide 18. To design perfect disturbance rejection and completely cancel the effect of DS on the output YS, the feedforward controller, GFF, must be the exact mathematical inverse of the plant dynamics relative to the disturbance. Step 1 is to set the disturbance numerator to 0. GD plus GP times GF times GFF times GM2 equals 0. Step 2 is to solve algebraically for the ideal feedforward equation, giving us GFF equals negative GD divided by GP. As noted perfectly in the text below, this assumes ideal valve and sensor dynamics, where GF equals 1 and GM2 equals 1. Moving to slide 19 for our stability analysis, we look at the characteristic equation. The crucial engineering insight here is that the roots of the characteristic equation dictate system stability. Because the feedforward elements do not appear in the denominator, adding FFC has literally zero impact on the closed-loop stability of the feedback system. Look through the magnifying glass graphic at the equation. 1 plus GP times GF times GC1 times GM1 equals 0. Notice the red arrow pointing out that the feedforward terms are entirely absent from the characteristic equation. The cyan variables GFF and GM2 are boldly crossed out with red X's on the flanks, guaranteeing zero impact on closed-loop stability. Finally, slide 20. The takeaway establishes that modern industrial automation requires a dual-layered approach. Feedforward absorbs the shock, feedback guarantees the destination. Let's discuss every single cell in this comparison table. For response timing, feedback, FBC, is reactive and slow. Feedforward, FFC, is preemptive and fast. The combined approach is optimized for both. For handles unmeasured errors, FBC is yes, FFC is no, combined is yes. For impact on stability, FBC determines it, FFC has none. The combined approach is handled natively by FBC. If we can map these exact, flawless, dual-layered, optimal control architectures onto vast industrial reactors, one has to wonder, how might employing this exact mathematical synthesis redefine our understanding of biological systems and human homeostasis? Something to think about. And as mandated, here is the final slide verification checklist. Slides processed, V. Slide 1, V. Slide 2, V. Slide 3, V. Slide 4, V. Slide 5, V. Slide 6, V. Slide 7, V. Slide 8, V. Slide 9, V. Slide 10, V. Slide 11, V. Slide 12, V. Slide 13, V. Slide 14, V. Slide 15, V. Slide 16, V. Slide 17, V. Slide 18, V. Slide 19, V. Slide 20, V. Total slides in PDF, 20. Total slides explained, 20. Skip slides, 0.